Our last, guys, you're responsible for the material whether it's covered or not. Okay? We've got to get moving here because there are things we've got to do. Okay, we've got to get through a couple of topics. All right. So, last pulley problem. Okay. 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 You'll excuse the crudeness of this drawing. I know. Okay, and then I'm going to come up to here, put another pulley up here. Okay, and I'm going to come down to here, say, where what I've got is this. Now let's assume. Let me just clarify that. I want to make it not as ridiculously complex. Okay. Okay. So there's this guy. We've got this, and then we've got our weight here. So this is all one unit of metal. I call this like a little ring up here, so it's attached to that. That's really horrible, but it's attached to that there. All right. All right. Let's just make it 15. Let's make it 50 newtons, just to make it easy. All right. So here's the question. So let's understand what's going on. We've got 3 pulleys, one individual pulley, and these other 2 pulleys are attached to this system where it's a frame, a little T-frame that attaches both pulleys and the weight. Okay? The rope goes from the ceiling all the way around the pulleys, back over, and attaches to the frame. Okay? The question is, what's the tension in the rope? The question is, what is the tension in the rope? Okay? The other question is, what is the reaction force, or the normal, I'm going to call this normal force 1. And this is going to be normal force 2. Okay? What do I know about normal force 2? What do I know it's equal to just by looking at this? It's equal to the tension in the rope, right? And the normal force 1 is equal to what? Is equal to what? Don't go let's not do quantitatively. Huh? Well, that tension in the rope of this pulley here, or whatever is pulling up here. Does that make sense? So the normal force 1 is equal to opposite of the tension up in this rope. Okay? So we're going to call this T1 and we'll call this T2. Does that make sense? You guys with me there? The tension, what's the tension right here? What's the tension in the rope right here, guys? In the rope right here, what's the tension? Not value, but is it what? It's T1, isn't it? Why is it T1? Yeah. If it's the same rope, then the tension throughout the rope is always the same, right? So if this is T1, what must the tension be over here? T1. Does that make sense? Okay, we talked about that yesterday. Think about that, right? That's the key. You got to know that. Okay. Now, how are we going to set this problem up to solve this? How are we going to set this problem up to solve it, guys? Yeah, we're drawing a picture, drawing some FBDs, right, from free body diagrams. Where can I draw the free body diagrams around?
The pulley where the comes from.
Okay, I can put it around each individual pulley. I can put it around the box. I can pull around the ceiling pieces. The issue is this: you need to have whatever your free body diagram box is. You have to have whatever's coming in it and out of it. Okay. You have to have something that you know and something that you. Okay, please put the balls up on my desk now. Put that whole container of balls on my desk. Dentino, the one in your hand, put the whole container of those balls on my desk now. Let's go, guys. Thank you. Whatever you need to be able to determine, you need to have something going into the box or out of the box that you know, and some things that you don't know, okay? And those things that you don't know, you need to be able to get to somewhere else. So for instance, okay, if I were to put a box here, I would know that T is coming out vertically, T is going out horizontally, but what else is coming out horizontally from this box? Yeah, the piece of metal. So there's a force in the piece of metal. So be careful about doing it this way because you're going to get in here a force that you probably won't know. Okay, because you have to start to get into that area. Ultimately, we're going to be looking for forces in the ropes. Okay? So what you can do is you can change this box and do this. And now what do I have physically coming out of that box? I've got either something that I know or something that I'm looking for, right? The force within the frame is not what I'm looking for. So that's one of the free body diagrams that I really want to use. Okay, so let's call this one number 1. So FBD1. Okay, and let's draw that. How could we simplify this scenario? Even though it's got 2 pulleys and a frame, how could we simplify this in terms of drawing wise? Well, we can make a simple drawing for this board. What shape?
Just a box.
Yeah, just a box. You can make a box. I mean, you can make it anything you want, right? But let's just make it a simple box, right? What do I have coming out of this box force-wise? Or physically, what do I have coming out of the box? So what are the physical objects coming out of this boundary layer of this free body diagram? How many rows? 3 rows. 1, 2, 3, and I have what?
The solid piece fits.
Yeah, which is really an extension of my weight, right? And because you know that the force coming out of here is going to be just like the rope. It's going to ultimately equal the force of the weight, right? So I have coming out the bottom, F of G, right? I have coming out of the top, what? Tension. Yeah, and 3T, right?
But it's all the same tension, right?
Yes, because it's the same rope. Yes, Ellie. Assume that the frame and the pulley itself doesn't have any weight. Okay? You can assume, unless I say differently, you can assume 2 things. 1, this is in a pulley system. It's not moving. And 2, all of the objects that are not called out as mass or weight are weightless. Okay? And if you have a question on the exam, you could say, I assume this to be massless, and therefore this is what I'm doing. But you can't assume that the 50 newtons is massless and change the problem. Ha 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 ha. Right? Okay, because then the tension would be 0, right? All right, okay. 0 for everything. All right.
But the answer is always 0.
Where did you get that from me?
Yeah, you said there.
Yeah, the sum is always equal to 0. You can always, I don't know. Yeah, the sum is always, look, everything always ultimately equals 0, right? Okay, what's my other, What is my other location I want to draw a free body diagram around? The other pulley. Okay. And so I'm going to call this number 2. Free body diagram 2. Okay. And I have what coming out of it? I have a rope. Where? I have a tension on the side. I got a tension on the side, don't I? And then I have another T2. These are all T1s, right? Sorry. And that's a T2. Right? Now, if there were mass to the pulley, we would have the force of gravity of the mass of the pulley, but we don't at this moment. We assume the pulley is massless.
And we just know it's T2 because it has to balance the T1.
Well, we know that this is a completely different rope than the other ropes. So we know it's a totally different T. You can call it T5, T5 million, pink elephant. It doesn't matter to me. As long as you don't call it the same thing, call the other T. Okay? All right. So how do we now deal with this? What do we go? Now that we've got our free body diagrams set up, what do we do next?
Solve for T.
Well, before we even solve for T, we have to do one thing first.
Equation.
We have to set up.
Equations.
There you go. We got to set our equation. We can create some equations. What are we going to solve? We haven't solved yet, right? So what is? How do I? Huh?
3T plus F.
So let's do sum of the forces in which direction? X or Y? Y. Okay. That's going to equal what? 3T plus FG. Okay, that's going to equal 0. What about this over here? Sum of the forces in what direction? Y equals, oh, that's T1, excuse me. 2T1 plus T2 equals 0. All right. Can I start working on this problem on the lower equation? No. No, I don't. But I do know something up here, don't I?
You know FG.
I know 3T1 plus a negative 50 newtons. Why is it negative?
Because it's going down.
There you go. Is T positive or negative? Positive. So T1 is equal to 15 newtons divided by 3.
Yeah.
Right? So I am a calculator baby, and I'm really sorry. So 16 and 2/3. Okay. So it's going to equal 16.7 newtons is my T1. Okay? Then I can plug that into here, and I can say, okay, 2 times 16.7 newtons, but is T1 negative or positive? Negative. Plus T2 equals 0. So T2 equals 37.2 newtons positive. 30, that's what I said, 33.4. That's exactly what I said. I'm like calculator, baby. I'm sorry. All right, does that make sense? Right? So it's 33.4 newtons. Easy? Easy peasy?
Yes.
Okay. Tomorrow we're going to do one where we have an angle pulling out. We're going to be pulling at an angle. Okay, I won't do that now. We'll deal with that tomorrow. I want to get on to friction. Okay?
Is this the set tomorrow then?
That's what's going to be on your problem set.
What, friction?
I'm going to give you some pulley problems and maybe some friction tomorrow. No. Okay.
But wait.
Yeah.
People want.
I don't have to. I can stay home. All right, what's the matter? What's the matter, guys? All right, can I erase this?
Actually,
Okay.
everyone here will do.
Yeah, we're doing it. Listen, there's a problem set. If you're here, you do it here. If you don't, then you've got to do it at home.
Cool.
Okay? So you're here, you get to work with your neighbors. Right? And your notes and everything else. You won't or will? Good. All right, I'm going to erase this. 3, 2, 1, erase. Okay. Okay, talk to me about friction. What do you guys think friction is? Conversation.
Like
Heat is a byproduct of friction. Go ahead.
the resistance to motion.
Okay.
It's like when an object is on something and it's trying to move.
Or when it's getting a force, but it doesn't feel the full effect of that force. Because there's another force pushing back and the force is friction.
Okay. There's a frictional force based on a frictional coefficient. Okay? So here's the deal. Let's think about if I had, let's say my iPhone cover, which is really pretty smooth, and the tabletop was really smooth. If it was perfectly, absolutely smooth, there would be no friction. It would just glide along. But right now, there is, it's not high friction, but there is some friction, right? If I push it, it's going to stop. Here's what it looks like. So even though I have a phone that's pretty smooth, sitting on a pretty smooth tabletop, okay, when you zoom in to this area, okay, you're going to get surfaces that look like this.
What is that supposed to be?
I'm looking into it. I'm looking in. It's like a magnifying glass.
Wait, what's a magnifying glass?
Here, I'm zooming in on this section.
Oh,
I'm zooming in on this section.
what are like the cracks in this?
Okay, the cracks, this stuff, if I were to zoom in with a microscope, you'd see that the surface is not flat. Okay? And so that's what it looks like. They are actually starting to mush together like this. And if I zoomed in yet again, okay, I zoomed in yet again, okay, it would look like I got one crack or one peak pushing against another peak. Do you guys see that? So ultimately, I'm trying to actually ride over, and the object kind of moves up and down very slightly. Okay, so this is what friction's going on. This is what we call friction. Okay, so friction, and I would have you guys do a lab, but I want to move forward and get to the next thing on this because I want to focus on the math and get to the next couple of things. We're running a little behind. But the issue is friction is just a coefficient. There are two types of frictions. Anyone know the different types of friction that there are? What's the different type of friction? Anyone know? All right, I do need a volunteer. Let's do a volunteer.
Me! Oh.
All right, so Tina. All right, Tina.
Can you jump rope? Oh, I thought you said something else.
Okay. All right, everyone go over and watch. Let's go. Let's do this really quick.
There's more space.
Have a seat. Put your ball on that. Have a seat on that. Okay, now.
How can you
All right, I need another volunteer.
Me!
Okay, sit him over here.
Oh, shoot
Okay.
it.
Okay, now, here's what we're going to do. There's going to be a point, and hold on tight, Dave. So we're going to do. I'm going to pull, and David's not going to move, right? Like it was for one
Oh, you said hold on.
Hold on. David, hold on tight. Okay? So at a certain point, David's not going to move. But after a certain point, David will move. Oh, this is not cool. Give me a big piece of cardboard up there.
Okay.
Go. Up. All right. Flat. Like a card. That's fine. All right.
Yes.
Wait, what it's like a cart?
All right.
A car.
I hope that's not the project.
It probably is.
It probably isn't.
You're right, probably
Have a
not.
seat.
Sit.
Have a seat.
Don't even worry. No.
No, but the other way.
That's fine.
Yeah.
Yeah.
Okay, there you go.
What?
All right.
Don't fall in.
Hold tight.
It's just gonna break. The cardboard.
Hold on.
No, like I was gonna lean
You
forward.
don't need more.
I
Be
won't.
on your knees.
Yeah, that's a bad idea.
Sit there.
I like this.
What am I supposed to do?
One thing it's working.
Okay.
Okay. All right. Okay. So here's the deal, guys. At a certain point, I'm pulling on David until what happens.
You start
But before that, what's he doing?
He's resisting.
He's not moving, right? Siva says that. So I'm pulling, and then he moves, and then I get some motion. Okay, Siva, I want you to do the same thing. I want you to pull straight. But I want you to feel the difference in force that it takes to get him to move versus the force that it takes to keep him moving. Come over here. The force you have to pull to get him to move, and the force it takes for you to continue to move him. Go. Come on.
Yeah.
Okay. All right, good.
Oh, shoot.
Are you okay?
Yeah.
All right.
Oh, it's hard.
All right. What did you notice? Once he started to move, what did you notice?
I thought it was easier.
Okay. It felt that was easy. Put that back.
That's just because I'm strong.
I don't know where you got this.
You leave it right there. Okay. So the issue is that there are two types of friction. There's a friction for being still to get you to move, and there's a friction once you're moving. Okay? Anyone know what these two frictions are called?
Stop friction.
Okay? Stop and move, but what's the actual term for them? Static and
Dynamic.
no, kinetic.
Oh, I was right.
Yeah, did you say kinetic? I didn't hear it.
I
Okay.
said
Oh, I didn't hear that. So static and kinetic. Static and kinetic friction. Shh. So I've got, okay, I have static friction and kinetic friction. Okay? So here's the deal. Static friction is the friction force you must overcome to get an object to move. Kinetic friction is the friction force you must overcome to keep an object moving. Does that make sense? Yeah, no, you can't read that. I'm so sorry. Static friction is the friction force you must overcome to get an object to move. Kinetic friction is the friction force you must overcome to keep an object moving. Okay? Here's a graph of friction force versus time. Okay? Here's what happens. From this point to this point, okay? Oops, excuse me. This is my friction force static, and this is my friction force kinetic. Notice that I have to overcome a larger amount of force, and notice this is interesting. My friction force isn't even though it's a static friction force, the static friction force isn't static. It changes. Right? Let's think about that for a minute. As I'm pulling Dentino and he doesn't move, Dentino, I pull a little bit. How much were you pulling back?
A little bit, not
Okay, then I start to pull more, but you haven't moved yet. How much are you pulling back? More. I'm pulling even more. You still haven't moved. What are you doing? Pulling back even more. His force equals my force. Okay? So the friction force that's keeping him in place changes based on how much I'm pulling on it. Does that make sense? It's a reactionary force. It's like a normal force, but it's a reactionary force. Until you overcome that force of friction and you start to move. And it drops down. That friction force, as you said, Siva, felt less. But it is now a constant force that you must overcome. And that friction force of kinetic friction never changes. The difference between static and kinetic friction force. The static friction force is always dynamic depending on how much you're applying to it until you overcome it. And then once you overcome it, the kinetic friction force is stagnant or consistent or constant as long as you don't go beyond, don't drop down beyond that force again. Yes, sir?
So you reach the kinetic friction point, then you start to like accelerate. Does
It
that
depends.
friction go up, or does it just like, stay the same?
Okay, this is the point right here of moving. Okay? I could, once I'm moving, and that means I'm moving, let me do it, let me draw it this way. That's moving. This is stopped. Okay? Now, stop means I have no velocity, no acceleration. Moving, however, do I clearly define whether I'm accelerating or have a constant velocity? No. So as long as I'm moving, I could have a velocity, or I could have a constant velocity, or I could have an acceleration. But again, it comes to that net force, right? So when I think about pulling an object, okay, I'm going to have a pull force and a friction force. If my pull, and let's say I'm moving, and that friction force is kinetic, then friction pull, if friction pull is equal to the friction kinetic, then I have no acceleration. If it's kinetic, am I stopped or am I moving? So what must my type of motion be if I have no acceleration? Constant velocity. Now, if my FP is greater than my friction of kinetic, then what am I doing?
You're accelerating.
Because in this case, my net force equals 0. In this case, my net force equals some number. Right? Does that make sense? And because force is equal to mass times acceleration, I'm obviously going to be accelerating.
Okay.
Does that make sense, everyone? Is that clear? Any questions on that? Okay. We're going to do two things. We're going to learn how to calculate the kinetic friction force, and then we're going to actually do some calculations with that. Now, here's the thing. The actual, let me come over here. So if I do, the equation for friction force is equal to the mu times the normal force. Mu of the normal force. Now this mu is going to either be mu of static or mu of kinetic. It's one of the two. Okay? It's just a coefficient. It's a percentage. It's a percentage. It's not even a percentage, it's a number. So it has some values here somewhere. Where are my values? Here we go. Yeah, it's a percentage, okay? So you're going to have a number, and these numbers are determined experimentally. Like the lab would have you do is determine some coefficient of frictions of different materials. If we have time, we'll do that. But I want to get through some pieces. So you determine these numbers experimentally, and it depends because I have different materials. These ridges are different on each material. So if I have one material and another material, I'm going to get one type of coefficient of friction. If I have the same material but a different material here, I'm going to have a different coefficient of friction, right? That makes sense. My shoes I wear every day work wonderful on this concrete. They do not work so wonderful on an icy surface, right? We all get that. Have my shoes changed? No. But if I change my shoes, I will then change the other material and maybe get a better coefficient of friction. Does that make sense? So the coefficient of friction depends on the two materials. And for each of those two materials, there is a static coefficient of friction and a kinetic coefficient of friction. Cool? Okay. The normal force. See, I told you it was going to come into account at some point. This is where it matters. When I have an object sitting on a table or something, right? It's just sitting there, right? I have the weight, F of G, and I have F of n. Okay? But F of n, what does normal mean, guys?
Perpendicular.
Perpendicular. Normal means perpendicular. Okay? So my friction force depends on my weight. Does it have surface area at all in here? Doesn't. Depends on the normal force, the amount of weight I have. Okay? So if I was trying to figure out the amount of force I need to overcome to move, this would be mu static. If it was the amount of force I need to overcome to continue to move, it would be kinetic. These numbers would be like, for instance, okay, wood on wood. Static coefficient is 0.4, or 40%. Coefficient for kinetic is 0.2. It's less. For metal on metal, it's 0.7 for static and 0.6 for kinetic. Rubber on dry concrete, 1 for static and 0.8 for kinetic. Okay? So those kinds of things. Does that make sense? Okay. And you'll be provided with that number, or you'll need to find that number based on the other information you have. Okay? Okay. So the difference, though, and we're going to get into this problem very quickly, is that what if this occurs? Is what needs to be corrected in this? Okay, let's change f of g. So you say f of g needs to go. Okay. What about the normal force? Does it change?
No.
Why not?
It's still pushing downward.
Bingo. Good. Good. I'm just going to move it. But yes, the normal force stays in its orientation because it's got to be normal to the surface pushing back. Okay? How much of from my first scenario, how much of my first scenario when it was straight up and down, how much was the normal force equal to? F of g.
Yeah.
In this case, how much is normal force equal to? What's something less than F of g, isn't it? Therefore, what does my friction force equal in this scenario versus the first one? Yeah, the friction goes down. Yeah, that's. Say again.
Oh, I'm saying because going down, the actual friction.
Yeah. Yeah, and that's why if I have an object, say, okay, the object is going to sit here, okay, and I can lift it up and lift it up and lift it up until eventually, what's holding it from falling right now? The friction, the static friction, and then eventually at a certain point it starts to fall. Okay, so and that friction force gets less and less because gravity is pulling more directionally down and less at the angle because this normal force is changing. The normal force changes based on my angle. Does that make sense? Okay. So let's do a quick problem. Cool? All right. Let's assume you've got a box, right? We've got our Tasmanian devil crate, right? I know it was cut poorly. It was made with like really simple tools. You can't really blame these guys. Come on now. All right. Now, all right. Okay. So let's assume that my coefficient of static friction is 0.6, and my coefficient of kinetic friction is 0.4. Okay? Let's assume that the mass of the crate is 10 kilograms. Okay? What I'd like you to do is tell me, what does F of P have to equal to move the box, to start it to move, and what does F of P have to equal to keep it moving? Go. Draw your free body diagram. Draw the free body diagram. Go, go, go. Draw the free body diagram, do your forces. What direction is your friction force going to work? What direction is your friction force going to work?
Opposite of the.
Opposite of F of P, right? Yeah, we're gonna. I'll write clear. I'm sorry. F of. Oh, hold on. Start. You mean up here? 10 kilograms. That's the mass of the crate.
You need to draw two for one to start. Moving.
Well, the free body diagram will be the same for both, right? Friction force is always going to be opposite your pull force.
Yeah.
But you would just use your value for friction force. That's why if you draw the free body diagram, you use FR, use a variable, then you can always change the number of the variable, right?
Okay, that's what I was wondering about. What label?
Yeah, you can label it however you want, but you can always label it one generic and then change it in your equation. Everyone know how to do this? Everyone can do this? It should be relatively simple. Everyone got a number?
Mr. Drake, do you use kilograms in the?
I can't hear you.
Can you use kilograms in the?
Gotta use forces in what units? Newtons, right?
Yeah. So kilograms.
Huh?
So kilograms in the equation. Like friction equals.
So remember, friction force equals mu times the normal force.
Okay.
So this is in newtons. It's newtons and newtons.
Okay.
F equals m times A, right? You've got to multiply your kilograms times your,
Acceleration.
yeah. Right, because you got to draw your free body diagram. Does everyone have a free body diagram?
Yeah.
Okay. Does anyone have an answer?
I thought we were just going to draw the shape of it.
Okay, now start to work the problem. Actually, solve for the numbers, guys. Solve for the numbers. Figure it out. And F of P, to start, these pull forces, are they minimum, maximum, or actual equal values? Minimum, right? In order to start moving, I need a minimum force to overcome friction. And to keep it going, I need a minimum force to overcome the kinetic friction. Kayla, do you have a number? Okay.
I don't think so, but
Well, check with someone. Check with someone. Make sure if you did it right. We're going to do it in a second. Okay, who's still working on this? Hmm?
Oh, I know.
Okay, so I've got a free body diagram up here, okay? And the free body diagram shows me that I have a couple of things going on. I've got two directions of force. I've got X and Y. I've got my normal force and my gravity force acting in opposite directions but vertically, and I have my pull force and my friction force acting horizontally in opposite directions. Is that clear? Everyone see that? Crystal, beautiful. Okay, then I can write two equations. I can write an equation for the sum of the forces in the y, and an equation for the sum of the forces in the x. Why am I doing the sum of the forces equation in the y? Why am I doing that? Why? What am I? Because I need the normal force, don't I? Right? And then why would I do the sum of the forces in the x?
Because that's how you find out what your pull has to be.
Okay. So let's figure out what my normal force is. So we assume it equals 0 vertically, right? Because we know it's not moving vertically. So f of g is equal to what? Negative 98.1 newtons plus f of n. So that's 0. So f of n is equal to 98.1 newtons, right?
Yeah.
Then I'm going to figure out my friction force. Well, my friction force is equal to, for static or kinetic, let's work on, let's say I'm trying to figure out how much I'm going to take to get it to move. I need the force, so I need my static, which is 0.6 times 98.1 newtons, which equals what? Someone? 58.9 newtons. So my pull force must be equal or greater than 58.9 newtons. And obviously, in this case, friction is going to be negative, right? Same thing for kinetic. We'll do some more of this in a problem set for tomorrow. All right.